Hello everyone, my name is Garrett Jares. I am a Ph.D. candidate at Texas A&M University in the Department of Aerospace Engineering. I work with Dr. John Vlasic as my graduate advisor. Prior to starting in aerospace engineering for my Ph.D., I actually received my bachelor's degree, also from Texas A&M, but actually in computer science with minors in cybersecurity and math, with most of that math work focused on cryptography. Transitioned into aerospace for my Ph.D., and so now my graduate research is kind of focused in between the two on aerospace cybersecurity in general. Today I'm going to be talking to you about my specific dissertation topic, which is control acquisition attack of aerospace systems via false data injection. So this talk is going to be kind of high level. We're not really going to go into all of the details of the work, and we're not really going to look at all the math behind everything. But we have previously published papers on this topic, and that does go into the details. So if you see anything in this presentation today that you want to learn more of, or if you're more interested in the work, I would point you towards those previously published papers, as well as some upcoming journal papers that we're going to have coming out soon. So what we're going to talk about today, I'm going to give you kind of a quick introduction to the problem. I'm going to take a minute and try to kind of set the scope. Make sure that we all know what we are talking about, what we're not talking about. And then I'm actually going to jump kind of straight to the end and show you some experimental results, kind of show you some flight testing videos and show you what we were able to accomplish using this method. Then we're going to go into the theoretical background. We're going to talk about how we actually produced those results, what we did, and why we did it that way. Then we'll wrap up with a few conclusions at the end. So jumping straight into the introduction. The problem that we're basically trying to approach in this work is investigating the possibility of a cyber attacker taking control of an air vehicle by intercepting and modifying the vehicle's sensor data. Basically, the attacker is going to fool the vehicle's controller into driving the vehicle as the attacker desires rather than as the victim desires. So this diagram at the bottom shows kind of just a standard, very generic feedback control loop. This is a diagram that describes how we typically control various states of a vehicle. So you have the reference signal coming in on the left side, and that reference signal is basically just where you want the vehicle's state to be, whatever particular state, whether you're trying to control altitude, pitch attitude, whatever. So that reference signal is going to come in, it's going to be combined with the sensor data, and that is going to be fed into the controller. The controller is going to make some decisions based on that data and send it to the vehicle. When we say send it to the vehicle, we mean that this is going to be actual control surface deflections that are going to then move the vehicle into a new state. That state is going to be measured by the sensors, fed back around the loop, and it just continues infinitely. That's why it's called a feedback loop. What we're doing in this work is basically injecting an attacker into this feedback signal. So the attacker is going to read in this sensor data, and it's going to send back some falsified sensor data that's going to go into the controller and manipulate the controller into driving the vehicle as the attacker desires rather than as the victim desires. So the idea is that the attacker is going to be able to drive the vehicle's state to its target rather than the reference signal. A good question, though, is why bother attacking this way, right? I mean, if we've hacked into the vehicle or into the ground control station or whatever, right? Why not just directly take over the vehicle, take over the control surfaces? Why not just send a different reference signal? And those are all very valid questions, but this approach provides some benefits. This is not meant to be, kind of the end-all, be-all solution. This is just kind of another tool in an attacker's tool belt that, again, kind of provides some benefits. Number one, this approach is very stealthy. This is because it essentially fools the vehicle into thinking that the vehicle is performing as it's supposed to be, when in reality it's doing what the attacker wants. Number two, this attack only needs access to the sensor data. And this basically allows you to attack the weakest link of the system. For example, the vehicle's flight computer might be very well secured and very well locked down, but the actual sensor itself might not be very secure. And so you could target the sensor. Or maybe the flight computer and the sensor are both secure, but the communication bus between them is not. Or maybe it's all secure, but the supply chain is not, right? This basically allows you to, like I said, attack the weakest link, because it doesn't matter where in the system you are as long as you have access to the sensor data and you can change it. Number 3, this attack can be done either on board or remotely. You know, there's stuff like GPS spoofing that would allow you to modify this data remotely. You could also, maybe install some malware on the system or on the ground control station or whatever. This kind of goes back to that attacking the weakest link point. It doesn't matter where or how you get the ability to manipulate the data, as long as you get that ability somehow. And then the last benefit, which is really the most important one here, is that this approach makes use of the work that's already been done by the vehicle's control engineers. Otherwise, the attacker would have to basically re-implement this entire control scheme from scratch, and that is a ton of work, and you have to know a lot about the system. In this approach that we're going to present in this work, we're going to see that we can basically exploit the fact that there's already a controller there, and just manipulate that controller to do what we want it to do instead of what the victim wants it to do. So I want to take a minute and kind of talk about the scope of this work, because what we are not trying to focus on in this work is any kind of specific implementation, any specific attack vector. We're not looking at vulnerabilities in any particular system or sensor. So we are not focused on applying this approach to a specific system and saying that this is how you could break into a system, you could exploit this vulnerability and install this attack in this way. That's not what we're focused on here. What we are focused on is developing a general approach to taking over a feedback control system, and we're doing that by injecting false data into the feedback signal. We're also going to look at flight experiments to test this approach against a real-world autopilot, but again, we are not hacking into this system, right? We're not exploiting any vulnerabilities or anything like that, right? So I just want to clarify that we are not focused on an attack vector. This work is focused on the development of the approach to take over the feedback control system by injecting the false data. So the assumptions that we're making in this work is, number 1, that the attacker has gained access to the feedback signal of the control loop. Again, this is kind of an abstract, concept, gaining access to the feedback control loop. Basically, we're assuming that somehow we have already hacked into the system and we have the ability to manipulate the sensor measurements. We're also going to go ahead and assume perfect sensor measurements, so no estimator in the loop, and that's just kind of a simplifying assumption to make things a little simpler here. Number 2, we're going to assume that the attacker only has access to the feedback signal. So the attacker doesn't know anything else about the model, the vehicle, the controller, or the victim command signal that's under attack here. We only have access to the feedback signal. Number 3, we're going to assume that the victim controller performs well and provides desirable characteristics. Basically what we're saying is that the controller that's already on board was designed well to fly this vehicle that we're taking over, and so we don't want to change it, we just want to use it to track our input instead of the victim's. And then number 4, for today we're going to assume that the victim has not implemented any kind of intrusion detection system that monitors the feedback signal. In the papers we do address the problem of an IDS, so I would direct you to that. But in the interest of time today, we're going to skip over that. We're just going to assume no IDS in the feedback signal. There has been some related work in this area, specifically some related work in false data injection. Most of this has been explored in the context of electrical power systems. And these kind of initial works basically demonstrated the concept of this false data injection attack. So these few equations here, this represents, so this y is equal to hx plus v, basically represents the regular standard sensor measurements. In this attack, these measurements are under attack, and they have this a vector, this attack vector, being added on. The whole point of this prior work is basically introducing this attack vector to change the state estimate x hat to some state estimate that is incorrect, x hat bad, and doing this while keeping the 2 norm of the error between the measurement and the true measurement and the true estimate equal to the 2 norm of the error between the bad estimate and the bad measurement, and keeping that 2 norm below some threshold. And this is because if that 2 norm goes above some threshold, then signals will go off. Will be detected by a bad data detector, and the vehicle will go into some kind of fail-safe mode or something like that. So basically, this initial work demonstrated that it is possible to inject this false data while avoiding detection from a bad data detector. Further work, developed more ways to avoid detection and kind of quantified the attacker's capabilities. And then other work has developed more elaborate detection methods and so on and so forth. And this work has also been applied to aviation and UAS in various different works that have developed the attack detection methods and simulated these attacks. Now, the most closely related to work to what we're going to be talking about today was shown in this paper. And this is a plot straight out of the paper. And basically what this work did was use false data injection that was, these false data injection approaches that were developed in prior work to attack a Boeing 747 model. And the important point about this work is that it focused on actually using this false data injection to manipulate the output of the system. Everything else before has focused on using false data injection to produce some bad estimate. But this actually used false data injection to produce an estimate that manipulated the output of the system. And that's what we're doing today as well. But so this plot, what it shows is the important thing to pay attention here to is the red line and the green line. So this plot shows the altitude from cruise. So this is basically plus 20 meters, minus 20 meters from cruise altitude. And we see at the beginning of this simulation that the vehicle takes off, or it doesn't take off, but it climbs from 0 meters, so at cruise, up to positive 20 meters, and it kind of settles there. And then we see when the attack is triggered that the attacker is able to actually drive the true position, shown there in red, down to negative 20 meters, so 20 meters below cruise altitude. But the feedback signal, shown in green, remains at that positive 20 meters for the duration of the simulation. So this shows that the attacker was able to actually come on and drive the vehicle down 40 meters while making the vehicle believe that it was continuing to fly at constant altitude. And so this is going to be pretty similar to what we're going to see today in the approach we're going to show today. But there are a few differences. Specifically, the novelty of the approach that we're going to be talking about today is, number one, this approach assumes that the attacker has no knowledge of the system. All prior work has assumed that the attacker either knows everything about the system under attack or at least something. This method relies only on access to the feedback signal. Number two, this approach investigates the conflict between the victim and the attacker control signals. Again, this is something that hasn't been explored in previous work. We're going to see that when the victim starts to introduce non-zero control signals, that creates some complications for the attacker. And in this work, we're actually going to develop methods by which the attacker can both exert its own control over the system and eliminate the control of the victim. And then number three, this work also demonstrates a false data injection attack on a real-world UAS in hardware experiments, which has not been done previously. So we're going to jump straight to the experiments and show some flight testing videos of what we accomplished. So these experiments were carried out on a DJI F450 quadrotor. This was flying the Pixhawk 2 Blue Cube with the Arducopter autopilot. And in this case, the attacker was actually implemented straight into the Arducopter firmware. So Arducopter is an open source autopilot. So we were able to actually get the source code. We were able to implement the attacker straight into the source and flash it to the Pixhawk. And it's also important to note that this was done within the state estimate. So as I said before, we're kind of assuming perfect measurements in the context of these hardware experiments. What that means is we're attacking the state estimate rather than the raw sensor data. And the purpose of these attacks is basically just to demonstrate and evaluate the performance of this attack on a real-world autopilot rather than just some controller in MATLAB, and on a real physical system. So the experiments focus on two test cases. In the first test case, the vehicle is going to take off to 5 meters, and the victim controller is going to attempt to hold the current position above the origin, basically. The attacker is going to come on, and it's going to attempt to drive the vehicle to a new position state of 5 meters downrange and 5 meters cross range. So that's going to be 5 meters forward and 5 meters to the right. In the second test case, it's basically going to be the opposite. The vehicle is going to take off to 5 meters, and the victim is going to attempt to fly to that 5-5 position, while the attacker is going to try to hold the vehicle at the origin. And we'll see that there's kind of a key difference between these two, and we'll see that as we go through these flights. So this is a video of the first flight test. So what you're looking at here is on the left. This is a down view. It's a camera that's mounted facing down from the vehicle. So we're looking down from the vehicle. And on the right, it's a ground view from an observer on the ground watching the vehicle. So we're going to see the vehicle take off. And in this case, it's going to reposition over the origin. And the victim is going to attempt to hold the position constant. So the vehicle is going to try to hold this position. The attacker is going to be triggered, and we're going to see that the vehicle flies forward and to the right. We're going to see that it oscillates a little bit, has a little bit of overshoot, and then it's going to come back and kind of settle at the attacker's set point. So what we saw was that the attacker came on and was able to actually drive the vehicle to that forward and right 5 meters position. The attacker is then turned off, the vehicle returns to its normal position, and then the pilot brings it down for a landing. So the video doesn't really look like too much, right? I mean, it's just the vehicle takes off, it flies forward and to the right. But what's really interesting is if you take a look at the plots, you can kind of see what's going on under the hood there, right? So these plots show the true position in blue, the target position in orange, and the feedback position in yellow. So you can see that the target position this whole time, this is where the victim is trying to hold the vehicle. You can see that it's just 0, constant the whole time. We also see that at the beginning of the simulation that all 3 of these positions are laid over on top of each other. That's because the victim is basically just holding that 0 position constant. And then we see when the attack is triggered that the feedback position, again that yellow line, is driven down by the attacker, and the victim responds by driving the true position of the vehicle up. So that's that blue line. And we can see that we settle, after about 15 seconds, that we settle to the attacker's target position of 5, while the feedback position settles to the victim's target value of 0. So this shows a really important point. It's that not only was the attacker able to drive the true position of the vehicle forward to its 5 meter set point, but it also fools the victim into thinking that the vehicle is now sitting at 0, at the victim's set point. So the attacker is able to fool the victim in addition to taking over the system. So this shows a very successful, attack by the attacker, and this is all great for the attacker. But if we take a look at the second test case, so this is going to be that same down view on the left, ground view on the right. And in this case, we're going to see the vehicle take off. It's going to reposition above the origin. And then in this case, the victim itself is going to try to make that 5 meters forward, 5 meters right set point. So the victim is going to try to fly forward to a waypoint, and the attacker is going to try to hold the vehicle over 0. So we see the vehicle flies forward and to the right a little bit, but then we see that motion kind of arrests, and we see it return back to the origin. And we see now that it's hovering above the origin at the attacker's set point. And so the attacker is able to actually drive the vehicle back to its target. At this point, the pilot cuts the attacker out of the loop. The vehicle returns to the victim's set point, and then the pilot regains control and brings it down for landing. So again, it doesn't really look like that much from the flight, but if we look at the plots, we can see what really happened here. So we see that in this case, the target position, which is the victim's reference signal, right? So that's the input from the victim. we see that it actually has this step input at around 5 seconds, steps up from 0 to 5 meters. Now I know that this isn't necessarily a true step input, but it's very close. If you have any questions about that, I would direct you towards the papers. It's explained fully there. But this is a kind of a pseudo step input at around 5 seconds. And we see that the true position of the vehicle kind of starts to follow that, and it goes up to about 2.5 meters forward before it's then turned around and brought back down to the attacker's set point of 0. We do see that, at the steady state that the attacker, shows a successful attack in this case. It's able to drive the true position to 0 while driving the feedback position to 5, so fooling, again, the victim into thinking that the vehicle did what it's supposed to. But we also see that, the attack in this case kind of has some limitations, because the attacker was trying to hold the system at 0 the entire time, and the victim was able to drive it away from that 0 position for a little bit there. It drove it halfway to the victim's input signal. And so this kind of shows one of the key weaknesses of the attacker here, and that's that the attacker will ultimately be able to, drive the system where it wants it to be, but it can never fully eliminate the attacker's input. The victim's input. So the attacker can, eventually have control of the system, but the victim is always going to retain some amount of control, and as the victim changes its input signal, we're going to see that true position will get kind of knocked off of where the attacker wants it to be. So those last couple of examples were pretty basic, right? Just kind of flying forward and to the right and showing a couple of plots. So I wanted to show something that resembles, this attack on an actual mission for a vehicle like this. So what we're going to see here is we're going to watch kind of two tests here. The first is going to be a benign mission, so there's absolutely no attacker in this case. And the vehicle is going to take off and it's going to fly in this square pattern. What you're seeing down in the left is a real-time plot of the true position, the target position, and the feedback position of this system. Right now they're all overlaid. We'll see in the second case when the attacker is on that they'll kind of diverge. But in this case, the victim's just flying in this square. It's flying over these 4 waypoints. And it's kind of just a very basic, simple square pattern to show you, this is what the vehicle's trying to do, and this is what it looks like with no attacker in the loop. So, again, vehicle just kind of flew in a square, very simple, very basic, no big deal. And then in this second case, we're going to actually have the attacker in the loop. So we're going to see the vehicle take off again. And in this case, the victim is going to try to fly that same square pattern, but the attacker is going to try to hold the vehicle over that first waypoint. And so we can see in the bottom left that all these positions are now diverging. We see that the true position of the vehicle, shown in red, is actually kind of hanging out over around the origin near that first waypoint where the attacker wants it to be. And we also see that the feedback position, shown in green, is kind of following. In fact, it's actually kind of leading the target position of the victim. So the victim is trying to make the vehicle fly where the blue X is going, flying this square. And it believes the whole time that the vehicle is flying where the green X is. So we can see that the victim actually believes that the vehicle flew in this square pattern. But we can see that the true position of the vehicle stayed over near the origin. And in fact, it flew in this kind of little star pattern rather than in the full square. And so the attacker, again, in this case was successful for the most part. It's able to keep the vehicle near its set point at over at that 0, position. And it is also able to fool the victim into thinking that the vehicle flew in this square circuit. Now, we do see, though, that the attacker, again, is not fully successful. If the perfect case for the attacker would have been that the vehicle just sat at that 0, position and never moved. But what we see in reality is that it flies in this kind of star pattern where that magenta line is outlined there. And so we see that the victim still retains some amount of control over this system, and it's able to knock the attacker off of its set point. And so that kind of just, again, highlights the weakness of this attack. Now we're going to see when we get into the theory that there's some things the attacker can do to kind of minimize the victim's control influence. But ultimately, as you can see here, it's never going to be able to completely eliminate it. So that was kind of just the results to kind of show you what we accomplished. So from here on out, it's going to be kind of the theory and some of the math. So if you're interested in kind of learning how we did what we showed you, then I would encourage you to stick around for the rest of this. But this is also has been published, and we also have some upcoming publications on this theory. So I would encourage you to check those out if you want, again, kind of all the details. So again, this is the problem statement. We've previously seen this slide, but I just want to show it again to kind of reiterate the problem statement. So the idea is that we're trying to inject this attacker into this feedback loop to read in the sensor data and send back this fake sensor data to manipulate the controller, right? If we put some variables to this, we can see that we have coming in on the left-hand side here this y sub v. That's actually going to be the victim's input. We see in the bottom right-hand corner the y sub a is the attacker's input. So those are the two reference signals, the attacker's reference signal and the victim's reference signal. And the attacker and the victim each, respectively, want the system output y of s, shown kind of in the top right corner of this block diagram. The attacker and the victim want y of s to go to their respective reference signals. So it's kind of a conflict between the attacker and the victim. The objective of the attacker in this case is to try and maximize its influence over the system output, but it also wants to kind of try and minimize its influence over, or minimize the changes that it's making to the feedback signal, f of s. And this is because large or anomalous changes in the feedback signal could result in detection. Again, we're not going to talk about detection today, so just kind of ignore that point, but it is addressed in the papers, and I would point you to that. So we can understand this objective a little bit better if we take a look at the transfer functions for y of s and f of s. So in this case, the attacker is actually implemented as a proportional controller. So it has a generic gain, k sub a sub p, the proportional attacker's gain. And if we implement this attacker, we can actually solve for the system output and feedback signals, and we get these two equations here. Now, the important result, though, is that if we choose the attacker's gain to be equal to 1, which is basically, no gain, these are the output and feedback equations that we get here. Now, the important thing to note here is that the attacker's reference signal, y sub a, shows up in the system output right next to the victim's input signal, y sub v. This means that the attacker has exactly as much control over the system as the victim does. And furthermore, the behavior of the system output, so the rest of that equation, remains exactly the same as if there was no attacker in the loop. If we got rid of that plus y sub a term, then the rest of this output equation would be just like there was no attacker in the loop. And so that shows a really important point, because the attacker hasn't changed the behavior of the system to the response. It's just introduced its own input signal, which is great, because now the attacker is able to exert as much control over the system as it wants without changing anything. But the problem is that the system output now tracks the sum of the victim input and the attacker input instead of just the attacker input like the attacker wants it to. So in this case, this attack actually demonstrates good control over the system, but it's unable to reject the control input of the victim. So to kind of illustrate this, this is a MATLAB plot. So this is just a simulation with a very generic, simple second-order system. And in this case, we implemented the attacker with a proportional control with a gain of 1. So what this plot shows is the attacker's input signal, which is that orange line held constant at 5 the entire time. And it shows the victim's input signal, which starts out as 0, but after 15 seconds steps up from 0 to 1. And so at the beginning, in kind of the first half of this simulation, we can see that the system output, which is the true output shown in green, is actually driven from its initial position of 0 up to the attacker's target state of 5. So this is good, successful attack by the attacker. And we also see that the feedback signal is driven up to 0, which is where the the victim thinks that the system should be. So again, good, successful attack by the attacker. But the problem is that at time step 15, the victim steps from 0 up to 1. The victim's input steps from 0 up to 1. And we see that the system responds by stepping from 5 up to 6. So it's now moved away from the attacker's set point, and the attacker can't bring it back. So we can't eliminate the control input of the victim, although we can introduce our own input from the attacker in this case. So the question for the attacker becomes how to remove the victim's control. Now these are the same output and feedback signals that we saw before. And in theory, this problem has a very simple solution. If the attacker were able to somehow know the victim's input, y sub v, then they could just choose their own input to be some y sub a sub d, which is their actual desired input, minus the victim's input, y sub v. If you plug this into our output equation, we get this output equation at the bottom here, this y sub s, or y of s. And we see that in this case, the victim's control has been completely eliminated, and the output tracks only the attacker's input. And the rest of the transfer function has not changed. So this shows basically perfect control of the system by the attacker, which is great. The problem, though, becomes how to find the victim's input. Now, the simplest solution would be that we could say, well, we'll just intercept the input signal similar to how the attacker intercepts the output signal. The problem, though, is that early on we made the assumption that the attacker only has access to the output signal. Now, if the attacker were somehow able to know the plant and controller, which is G of S and D of S, they could actually solve for the input equation, y sub v. But the problem is, again, we assume that we only know the output. Excuse me. But the reason why I put this on a separate bullet is because it might be possible for the attacker to try and estimate G of S and D of S using system identification or parameter identification methods. And so it might be possible for the attacker to actually estimate those equations and then get an estimate for the victim's input and use that to eliminate the victim's input. That's not within the scope of this work. I think it'd be an interesting topic for future work. But I think that's just an interesting point. The last option that the attacker has is that it could solve for the victim's input at steady state. So we know that at steady state, the output tracks the sum of the victim's input and the attacker's input. But the problem in this case is that the attacker actually has to wait for steady state to occur, and that could take a long time and still get all of the victim's input put into the system. So an alternate solution that we're proposing in this work is that the attacker could implement integral control. If the attacker were to implement a proportional integral controller as the attack, we get the output equation shown here. We can use the final value theorem to show that the steady state value goes to the attacker's input and completely eliminates the victim's input. Now the problem, though, is that the transient response of integral control is very slow, and it's not fast enough to eliminate in the transient, right? It's not fast enough to keep up with the victim's proportional control. So, but what's interesting is that if we actually go back to the proportional only attacker, we can show that at steady state, we get this y steady state shown here at the bottom, which is 1 over k sub a sub p times y sub v plus y sub a. And so this shows that as the attacker's proportional gain is increased, the victim's control over the system is decreased. So if the attacker were to implement its gain as 2, then only half of the victim's input would show up at steady state in the output. If it were to increase its gain up to 10, then we would cut the victim's control down to 1/10. And so the attacker can basically increase this gain to eliminate most of the victim's input, and then add on some integral control to eliminate the rest of that input slowly over time. And that is basically the approach that we're using in this work. So to kind of illustrate this, this is the same simulation that we just saw. But in this case, the attacker has actually implemented a proportional integral controller. And it's also increased the proportional gain from 1 up to 2. So what we see in this case is very similar at the beginning. We see that the attacker is able to drive the system output up to its target state of 5 and drive the feedback signal up to the victim's target of 0. But what's interesting is that at 15 seconds, when the victim steps from 0 up to 1, we see that the output signal is again kind of knocked off of the attacker's set point, but we see that it only goes halfway up toward it only includes half the contribution of the victim input, and then that integral control slowly returns it to the attacker's set point. So we see that the attacker, over the course of this whole simulation, is able to drive the system to its target state, and then whenever the victim tries to give some input, we see that it bumps the system off of the attacker's input, and then it's returned. So the attacker is able to hold pretty close to that value for the entire duration of the simulation. So in this case, the attacker demonstrates both control over the system and rejection of the victim control, which is good. This is basically what the attacker wants to exert. So this is a good, sufficient solution for the attacker, and the attacker can basically increase these gains to increase how much rejection they want to include here. So just to wrap up with a couple of quick conclusions. We've shown that we can use proportional integral control to perform a control acquisition attack on an unmanned system. The proportional term exerts the attacker's control, and then increasing the proportional term and introducing the integral term serves to remove the victims. Also, this attack can be performed with no knowledge of the system under attack. It only acts on the error between the attacker's input signal and the system output. It has no knowledge of the plant, controller, or the victim input. Some of the continuing work that we're working on as we move forward with this is analyzing the effects of this attack on the stability, controllability, and observability of the system. Determining some metrics, bounds, and guarantees about the attacker's performance. I know that that's kind of a generic statement, but basically we're just trying to identify the conditions where the attacker is successful and those where it fails. We're also investigating this attack in the presence of disturbance rejection controls, such as H-infinity. And we're further testing different conditions in the experimental results, so different combinations of the attacker input signal, victim input signal, and the attacker gains and the magnitudes of those input signals. Just as a final acknowledgement, this research was funded by the National Science Foundation Graduate Research Fellowship Program, and the authors gratefully appreciate this support. Thank you, and if you have any questions, feel free to reach out to my advisor, Dr. John Velasic, either at his email, velasic@tamu.edu, or you can check us out on our webpage at vscl.tamu.edu. Thank you.